forget, if you would like to, you don't have to, of course. If you want where's here we go. Don't forget, you can download this book. It's just don't share it with anybody, or don't. I'm not so concerned about that. I just don't want it out there saying, "Hey, free book here for everybody" on social media or something. So the publisher will wonder, how that happened. Okay, but it's there for you to download. If you want access to it. Oops, anyway, it's there for you to download.
Thank you, Rick. I was just wondering, in terms of like the PowerPoints, is there a way to just streamline the download, or do you just have to from Canvas, or you just have to go through one by one, probably?
One by one, I could try. What I can try and do is put them in a zip file.
Oh, okay. If you have time,
Yeah,
but don't worry about it if you don't.
Yeah, I'll put that up there.
Thank you.
But isn't it more fun to just do it one by one and wait? No, I'll put it in a zip file.
Thank you. Okay, but no pressure. We'll work around.
It's things like that. It's like, oh yeah, that makes sense.
Great.
Yeah.
Thank you.
Sure. No, thank you. Sometimes I never think of the easy way of doing things. Yeah.
Well, the system isn't set up for that on Canvas, so yeah.
Yeah, and Canvas is kind of, I've tried to use Canvas. I'm changing, you'll see next semester in CIS 82, I am changing Canvas and my syllabus, how I do things in Canvas. Things will be organized differently. Because I've always, for years I used a website. We had websites. And then we no longer can use websites. And that's not uncommon, at least in California. Many schools no longer allow faculty to have websites for various reasons. One of them is they have to make sure that accessibility, anything on a website that's part of the school has to be accessible, meet accessible standards. Now, why, Canvas is different, I don't know. And there's also some other things I worry about, security and things like that. So they just, even at UCSC, we don't have our own, there's a template you can use. But other than that, they've basically kind of taken away websites. So anyway, my format has always been kind of to look like a website in Canvas, and that doesn't work real well. All right, so let's get to today. Today, what I want to do is finish up kind of the neighbor solicitation, neighbor advertisement, talk about the neighbor cache, which is like the ARP table, okay? When in IPv4, now here's my Mac here, and it's the same command on Windows, but if I do ARP-A, shows you my ARP table. Well, let me do it like this. ARP-A, I'm going to do, you just need to do ARP-A. I'm just going to show it. How do you spell ARP? Did they change the spelling of ARP? There we go. Address Resolution Protocol. I'm using the grep. This is on Linux or Mac OS to show you just my Ethernet interface. But basically, it's a mapping of IPv4 addresses to MAC addresses. So, when my device knows the IPv4 address but doesn't know the MAC address of where it wants to send something to, it does an ARP request, get the ARP reply, put the MAC address in the MAC address in the ARP table. So similar with ARP, similar with IPv6, call it neighbor cache. We talked about neighbor solicitation and neighbor advertisement message. So I'm going to do this quickly, and hopefully I didn't make any mistakes because I just took an older Wireshark entry and modified it. So we'll catch Rick if he made any mistakes here. But here we have router R1, and I'm going to use the router here because we're going to look on Cisco iOS and look at how we can see look at the neighbor cache in a little bit more detail. I'll get there in a moment. But let's say this router has a packet to send to this PC here. It knows its IP address, but it needs to know its MAC address because it needs to encapsulate this packet in an Ethernet frame and send it to the MAC address of the PC. Okay. So this is where hopefully I did things right here. You know, make this a little smaller, get rid of this. So we can see this here. We don't need use them. Okay, so this R1 is sending the neighbor solicitation message. Okay, so it's saying, I'm looking for this address right here. First of all, it's an ICMPv6 message. Okay, 135 means neighbor solicitation. Type 35, code 0 is a neighbor solicitation message. Okay, similar to an ARP request. This is the IPv6 address. I know it's IPv6 address, but I'm looking for its MAC address. By the way, here is my MAC address. So this is R1 sending this out. Okay, it gets encapsulated in IPv6 header. Okay, the next header field points to saying, hey, this is an ICMP, I'm carrying ICMP message. This is the global unicast address of the router. And this is the destination IPv6 address of the device it's looking for. Now, it's using a solicited node multicast address. Why is that? Okay, well, the reason is it's taken this IPv6 address that it knows, and it took the last 24 bits and put it right here, and then added the rest of this, which is a solicited node multicast. Okay, it then converted this into a destination MAC address. So 3333 is a multicast. And what it did is it took these last 24 bits, really 32 using FF, and mapped it to this. So all these devices on this network are going to get this Ethernet frame, but only devices that have a NIC card that accepting a multicast address, where basically any devices on this local area network that have a unicast address that maps to the last 24 bits of this MAC address, meaning they have a unicast address that maps to the last 24 bits. They're the only ones that will accept at the hardware level, at the Ethernet NIC card level, accept this Ethernet frame. And that was perceived as a benefit for IPv6, that other network interface cards don't have to look at, well, they'll see it, but they don't have, they can, the network, other devices, network interface cards can go, nope, that's not me. I can stop this at the NIC. I don't have to send this up to a higher level process. Yeah. All right, so all those devices would get it. Hopefully they all, anybody, only those devices have this exact 24 bits here, say as a unicast address would accept this. Now let's assume nobody else really has 017086. So this device says, yes, this would map one of my multicast addresses that I need to accept on the NIC card, because I do have a device that maps to this. All right, so then what it's going to do is send back a neighbor advertisement message. Okay, again, another ICMPv6 message, type 136 code 0. It's saying, okay, here is my IPv6 address that you knew, and here's my MAC address. This is what you need. This is what you've been waiting for. So this is the WinPC sending this back. Okay. The IPv6 says, okay, the next header field, ICMPv6, source address. This is coming from me. And you gave me your you gave me your global unicast address. Okay? I saw that. And you know what? You also gave me in your neighbor solicitation message, you gave me your MAC address. That was part of the neighbor solicitation message that R1 sent, just like it does in IPv4 with an ARP request. The sender neighbor solicitation message or ARP request in IPv4 always includes its own MAC address. So the other side says, oh, I can put this in an Ethernet frame and send it to you. Yeah. All right, so that's how all of this works. Very similar to ARP, just has this kind of multicast stuff in the middle. All right, let's extend this a little bit here. Make it a little bigger so we can see. That's better. All right, so what we're going to look at is what happens after it receives this neighbor advertisement. It goes into something called a neighbor cache. Now in ARP is very kind of more straightforward. Bringing up my ARP table here. Okay, ARP and IPv4 is very much more straightforward. So this is the ARP table IPv4. It's basically an IPv4 address, and then we learn the MAC address. Okay, yeah, that's it. It's either there or it isn't. Well, let's take a look. IPv6. Of course, they had to make things a little bit more, too many cooks sometimes, but maybe it's a good thing. We're going to look at the neighbor cache. So let's go through this, right? Yeah. So let's look at the neighbor cache for IPv6. So first of all, I'm on a router. Okay, I'm on a Cisco router. I'm going to do clear IPv6 neighbors. That's clearing the neighbor cache, similar to an ARP cache or ARP table. I'm going to do show IPv6 neighbors. That's looking at the ARP cache or the neighbor cache. It's called the NDP cache. We'll look at this in a moment. So this is it here. It says there's nothing in there. It's empty. Okay, because I just cleared it. Now, if I ping, this is the router pinging that device. Okay, so what it's going to do is send a neighbor solicitation. You get the neighbor advertisement. Okay, then we'll be able to send the packets encapsulated in the destination MAC address associated with this IP address because we're on the same network. And now if I did show IPv6 neighbors, here's my neighbor cache. Okay, there's the IPv6 address that I already knew about. And there's its MAC address. But it has something called a state. Okay, and that's what we're going to talk about today, or this morning, is this state. It's in the reachable state. Okay, so let's take a look at this. If 30 seconds later, so notice that right now I'm in the reachable state. Okay, 30 seconds later, I do show IPv6 neighbors, and notice that state is now stale. Stale. IPv4, I don't see nothing gets stale in IPv4. What's that mean? We'll talk about that in a moment. Okay, if I ping it again, and the pings all work, okay, do this show IPv6 neighbors again, and now it's back to reachable. Okay, so what is all this? Let's take a look. I'm going to put my chat over here so I don't miss any chats. There we go. Okay. What's this stale? What's this reachable? What's this state thing and IPv6 neighbor cache? All right, so we saw that the show IPv6 neighbors. This is what we use in on Cisco iOS to look at the neighbor cache, the ARP cache. Okay, we'll take a look at it on a PC here in a moment. Okay, no entry. So first of all, if there's no entries, okay, that's when we cleared it. When we did that ping, okay, and we'll go through this here in a moment. What happens is, first thing my router had to do was find out, hey, there's no entries in my, we say no entry exists for that IPv6 address, or in this case, none, but for what we're looking for. Let me bring that up again. Here we go. So when this device we did a ping for this IPv6 address, this MAC address was not in its neighbor cache. Leave this off to the side there. In case we need it. There we go. Okay. So what it did was it sent out neighbor solicitation message. We saw that, sent out neighbor solicitation message. Okay. That's when it goes into a state called incomplete. Okay. And you may not even see this. Sometimes you will, but you may only see it for a short time. Okay. It's in the incomplete state. If up to 3 neighbor solicitation messages are sent and there's no neighbor advertisement, so it sends the neighbor solicitation, doesn't hear, sends it again, doesn't hear response, sends it again, no response. I mean, no response, no neighbor advertisement message. If it never receives a neighbor advertisement message, okay, then it will no entry. It just stays blank. It goes back to, removes this as an incomplete entry and removes any mention. The incomplete would actually show the IPv6 address and it would actually say incomplete, meaning it's waiting for the resolution of the known IPv6 address to a MAC address. When it goes back to no entry exists, it will be removed. Okay? But in our case, we sent out a neighbor solicitation. Hey, we got a neighbor advertisement message in return. So when the neighbor advertisement message is returned, that's when this entry now it's in the table and it's as reachable. Okay, so that's when we saw it as reachable. Now, how long does it stay in there as it reachable? It stays in there for 30 seconds. Remember? We waited 30 seconds. And after 30 seconds, it's still in the table, but it goes from reachable to stale. It just means, there's been no communication with this device for 30 seconds, but it's still in the table. Okay. Now it will stay stale in the table until another packet is sent for that device. Okay. If all of a sudden, and this is what happened to us, it was stale, we did another ping, and now it would go into what's known as delay state. And we're going to see this here in a moment. Okay, delay state. It says, oh, wait a minute, something's happening. Let's see if it's out there. If packet is returned, okay, then it will go to reachable. So when we got those pings coming back, it will go reachable. Don't worry about this TCP increasing ACK stuff, okay? Has to do with an ongoing connection. Every time you get an acknowledgement in a TCP connection, when you're constantly communicating with a device, you're getting acknowledgements. Yeah. All right. But let's say that we don't hear anything back. Okay. Then what will happen is we'll go into it will start probing. What happens here is it starts sending neighbor solicitation messages again. So it says, oh, wait a minute. I haven't heard from you. Okay. So I'm going to send out another neighbor solicitation message. If I receive a neighbor advertisement message, you're reachable. If I don't hear back from you, then you're no longer there. Maybe, you got turned off, shut down, whatever. Let's see how this works. We can see how this works with debug IPv6 ND. Now, how much of this is really all that important? Probably the only thing that's really important here is reachable and stale. or it's not there. So just notice that those just, and we'll see, talk about this more in a moment. In IPv4, you know, it's either there or it isn't. It's just that in IPv6, if I do the same command, what's important for us to recognize here is just that you're going to see some state information. It's coming. It takes a moment here because I got all these different interfaces running. Okay. Well, let's see. I've got to ping something here. These are all permanent entries here. Let me see if I can ping one. There we go. Oh, there's my default gateway. Okay, I didn't see it. All right, let it do its thing here. So here's my default gateway. Okay, so what it's showing here is in Mac OS, what it does is it actually shows a time. Okay. Come on, you can do this a little faster here. Okay, you're gonna see here, this is the states. R for reachable, D for delayed. So it was in the delay state as it was going from, now it's back to reachable state. And how long it's counting down. So let's take a look. It's a little easier to see this on here. Okay, so what I'm gonna do is I'm on router R1. I'm just gonna clear the neighbor table. There's nothing in there. Okay, I'm gonna run debug IPv6 ND. This will give us really what we need to know at a higher level. Okay, we pinged the device. So let's take a look at what happened when we did debug IPv6 ND and what happened during this process. Okay, what happened was we could see it's gone from delete, which no entry exists, to incomplete. Okay, then the device the router started sending neighbor solicitation messages. So it shows sending neighbor solicitation message. Okay, it says, oh, I sent a neighbor solicitation message. I did get a neighbor advertisement message from it, received neighbor advertisement. So now this is showing that it got that's not local address. It's not terrible. This is the layer 2 address of the device. It's saying I did get its MAC address. And so I've gone from incomplete to reachable. This is just telling me it's now in the table as reachable. I do show IPv6 neighbors and I can see it in the table as reachable. I say this is terrible because LLA, they don't mean link local address, they mean layer 2 address. So link layer address is what they're talking about. Terrible on Cisco iOS to use the same acronym for two things. Okay, so now we see that have the IPv6 address and now know the MAC address. After 30 seconds, we're still running debug IPv6 ND. So it tells us that our state went from reachable to stale. Okay. Matter of fact, if I do show IPv6 neighbors, I see that it's now stale. Okay. You can see this same information, by the way, in Windows, NetSH interface IPv6 show neighbors. Linux IP-6 neighbor show, Mac OS NDP-A. I wish Windows just made it a lot easier, but they don't. Cisco iOS show IPv6 neighbors. Now let's see what happens when this computer goes down. It's been shut down. Okay. So let's do a debug here. So it's stale right now. Okay, I go to ping it. Okay, and Of course, this device is down, my router goes, I'm not hearing anything back. Let's see what happened. So when we shut down that device, okay, and we tried to ping it. So we had R1 trying to ping this device. Okay, so we were in stale and now it's in the delay state. Okay, and it said, I'm not getting packets back. Let me do a probe. Okay, so I didn't get anything back. So I'm in the probe state. And the device, R1 in this case, sends out another neighbor solicitation message, another ARP request. It says, hey, who out there is this IPv6 address? Since you didn't respond to the ping, the echo request with an echo reply, maybe you have another MAC address. So that's kind of the cool thing about this. It will keep the MAC address and says, oh, wait a minute, if there's no response from the device, maybe you got a new MAC address. So it sends out a new neighbor solicitation message. Okay. Let me finish this here. Now I'll get back to what I just said. Sends out a new neighbor solicitation message. Okay. Sends out 3 of them. Okay. No reply. It would only send out 1, but it never got a reply. So it didn't get a reply, No neighbor advertisement coming back. Okay. So it goes from probe to delete, and it removes the entry. Removes the entry from the neighbor cache. Matter of fact, we'll turn off the debug now, and do show IPv6 neighbors, and it's no longer a neighbor. The whole idea of having this address in its table, even as stale. So let me go back here a moment. Even as stale. And then what can happen is, what if you assigned a server, a router, same IP address, but you took down an old device, server, router, put in a new device, same IPv6 address, but different MAC address. So it would still be in the table. The IPv6 address would still be in the table. It would be stale. But as soon as that device tried to communicate with it, it would say, hey, you're not answering the ping, whatever. Okay, no problem. Maybe you have a new MAC address. So that's why I would send out the new neighbor solicitation message. Hey, who out there is this IPv6 address? Give me your MAC address. In the case where we actually replaced the device, same IPv6 address, different MAC address, it would actually reply saying, hey, here's my MAC address. So it allows for that. So there's a lot happening under underneath all this. So again, more knobs, only in case we need those knobs. But for the most part, all we're really concerned about is reachable, stale, or it's not there. Reachable just means that we've communicated with that device in the last 30 seconds. Stale means we haven't, we once communicated with it, it hasn't been there for the last 30 seconds. No entry exists means we haven't communicated with that device.
Rick, could I ask I'm sorry, I was just going to ask a quick question about the debug. When we debug, what all are we getting or looking to get from that?
So debug is, let me show you this. So debug IPv6 ND, that is a command that says, matter of fact, let me do this. Let me log into our router here. Second here, I'm going to log into our router.
Because it seems like by the nature of the definition of debug, it would be more like removing things, right? But it's not doing that.
No, I mean, debug means show me the details in this context.
Okay, got it. Thank you.
Mm-hmm. So let me show you. That's a good question. Oh. Da, 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 da. The world, no, that's. There we go. I'm gonna log in here. Okay. So I'm on our layer 3 switch here, and you go into privileged exec mode. There we go. So debug. Debug is a very useful tool. You know, it's similar to Wireshark in that it can give you a lot of information, but sometimes it gives you too much information. And you also got to be careful with debug in that if you get way too much information, that you can actually overload the CPU of the device. So, for example, you never want to do this on a production network. I'm not going to do that. That means debug anything that's going on. See all this stuff here? Debug all of this stuff. Anything going on. Okay. That's something we don't want to do. If I go up to here for debug IP, so that's IPv4 as opposed to IPv6. But if I was to do debug IP and see what the options are there, there's a lot of options there as well, including debug IP packet. That means, tell me about every packet coming in and out. That can I mean, you're talking about routers that sometimes handle hundreds of thousands of packets per second. That can bring down the router, just what it's having to look at. So you want to be very careful. But we're going to do debug IPv6. Now, what's some of my options with IPv6? Some of my options, as you can see here, OSPF, we're running OSPF. I can look at all packets. I got to be careful with that. But ND, that's what we just looked at, neighbor discovery. Let's see if I have any options. Okay. I don't really have any good options. So I'm just going to hit CR for carriage return. Now this will give me everything we just saw here. Okay. This is anything with neighbor discovery. So what is included in neighbor discovery? Neighbor discovery includes 5 things: router advertisement messages, router solicitation messages. So that's all that, hey, who out there's an IPv6 router? Hey, I'm an IPv6 router, and it sends that router advertisement message out constantly. Neighbor discovery messages, this is all ICMPv6, includes what we've been seeing with neighbor solicitation, neighbor advertisement messages, which hosts are quite chatty about. They want to know who else is out there, you know, especially with things like multicast DNS, you know, hey, do I have a printer out there that maybe I'd like to know about? And then there's one more I'll talk about too. Well, there's that we'll talk about here in a moment is the redirect message. So if I hit enter here, you're going to see neighbor discovery stuff happening. Oh, there we go. I had to send it to terminal monitor or something. I'm on SSH. So this means send it to my SSH session. So you see all this stuff, a lot going on. See all this probe, reach, neighbor sending, neighbor solicitation, receive neighbor advertisement. This is all the chattiness that's happening. Okay, with all the devices, I'm on one of the networks here. So you can see all this reachable stale. So this is telling me everything that's happening with, this router, on all the different networks. So let me do an undebug all here, so don't, okay. Terminal no monitor. There we go. One of those weird commands where the no comes right there. This is our layer 3 router. This handles all the IPv6 networks in the upper part of the 800 building, the classrooms, offices, data center. So this is showing all the for different networks, not just one network. So before we saw it just right here, but this would be showing it for every network that this router is connected to. That's what we're seeing here. Okay. So we're seeing all kinds of neighbor advertisement, neighbor solicitation messages coming in and out of this router. We are seeing any changes in its neighbor table, going from reachable to stale, back to reachable, stale maybe to entry no longer exists, any of this stuff. Somebody's ARPing, going from it's sending an ARP, a neighbor solicitation message, going for no entry exists to incomplete to reachable. So we're seeing all of this for all the different interfaces attached to this layer 3 switch, this router. We're also seeing any router advertisement messages that are being sent. See if I can find one real quick. Sending router advertisement message. This is for one of the networks. Say this is the prefix. There's the A flag. Create your own prefix, sending it out every 200 seconds. So that's what we're seeing. Does that, I know I more than gave you, more than you asked for, but does that kind of make sense with the debug?
Yeah, that was extremely helpful. Thank you.
No, yeah, you're welcome. Great question. I like to take the opportunity to, show something real, how we use this kind of stuff. Again, debug you want to be careful with, okay? That you don't, bring down the route. I've done the wrong debug command, and it's actually, and had to go and physically turn off the router. By the way, there are ways, and I'm just going to throw this out there. So I did debug IPv6 ND. There's ways that you can create access control lists. We haven't gotten into this. This is something I talked about in CIS 83. But we don't even talk about it with debug. But we do talk about access control lists. There are ways that you can run a debug against what we call an access control list. So instead of seeing all of this stuff that I'm seeing here, what if I just want to see things coming, maybe neighbor solicitation, neighbor advertisement messages coming out of a specific interface? Okay, so yes, what I'm getting at is I can limit what I see in a debug, kind of like, grep in using my Linux or Mac OS commands, Unix commands, so I can limit what I see. Kind of giving a quick analogy. Sorry if I'm taking too long on this. If I did, let's just use ARP-A. If I do ARP-A, I'm going to see my ARP table for all of my interfaces. This includes my Ethernet, Wi-Fi, and everything else, EN7, EN0, and anything else. If I wanted to just see it just for my EN7, my Ethernet physical interface, EN0 is my Wi-Fi interface, then I can use this filters it. So I can use access lists to filter what I see in debug as well. One more kind of slide I just want to mention on ICMPv6, and we'll take a short break and we'll start looking at ICMP echo requests and echo replies. This is all part of neighbor discovery. So one thing about that devices, whenever have a link local address or a global unicast address, temporary, permanent, whatever, before a device uses an IPv6 address, it has the option of using something called DAD, duplicate address detection. And basically what that is, let's say this device just booted up and gave itself an IPv6 link local address. And it puts it in what's called tentative state, meaning, this is going to be my link local address. Before I use it, I'm a little tentative. I want to make sure that nobody else is using it. So what it sends out a neighbor solicitation message. Hey, is anybody out there have this IPv6 address? Send me your MAC address. Okay. And if nobody replies, which is what it hopes for, then it says, hey, I can now use this address. Nobody sends back a neighbor advertisement message. So this device here would send out a neighbor solicitation message. So here's the address. It says, anybody have this address? This is in the ICMPv6 header. Or ICMPv6, header. This would be the target address. And it says, here's my MAC address, by the way. And I'm sending this out, okay? Now what if it's sending it from a link local address? It doesn't have another address yet. It doesn't have a global unicast address yet because it wants to make sure, first of all, it's doing, it's going to, it hasn't sent out a router solicitation message or hasn't gotten a router advertisement message. Okay, gonna do this first. It can send it from an unspecified address. What's an unspecified address? It's the double colon. Okay, it's the all zeros address. And basically, it's sending it to this multicast address, but basically sending out this neighbor solicitation message asking who has this IPv6 address. It waits a certain amount of time. If nobody replies, then it says, great, then I know this is good. If it gets a reply, now where would it get the reply to? It would be sent, remember this device sent its MAC address. So the Ethernet frame would still be sent to the MAC address of this device in the neighbor advertisement message. But it hopes it's not going to get that. And if it doesn't get any kind of neighbor advertisement message, then it says, hey, I know you're good to go. By the way, I know we're covering a lot of things, a lot of different things. Next Tuesday, I'm going to bring all of this together. Okay. So using both Packet Tracer and what I'm doing live on here on our network here at school. We're going to review everything, kind of bring it all together, how it all fits in. All right, let's do this. Let's take a break. And what we're going to do is let's take 8 minutes, come back, and I'm going to talk a little bit about ICMP echo request, ICMP echo reply. I'm going to do a Wireshark. To learn a little bit more than we did in I-81 about echo requests and echo replies, the ping. Okay, so let's take an 8-minute break and remind Rick to start the recording. Be right back.
Recording stopped.
We're right with everybody here.
Rick, Rick, I have a question.
Yeah.
Earlier, you told me the program you used to SSH. I forget what it was, but it's not a free program.
Well, SSH isn't a program. SSH is a protocol.
Yeah, I know that, but the program you
Zoc is not
Yeah.
free. No.
yeah. So another question is, so
No.
I should be able to SSH into my own router.
Not necessarily. So
Okay.
SSH, it's a good question. So first of all, there are free programs out there if you have Windows device. PuTTY is free. There used to be something TerraTerm. I think that's still out there. John might know of something for Linux or Mac OS, which is Unix, that is free.
So there is a Mac does come with a command line SSH.
You can use
program.
command line. Yes.
Okay, I'm okay
Yeah,
with that.
yeah. So if you're comfortable with that, that's fine.
But I cannot log into my. I cannot
Well, when you
SSH.
say your router, is this your router? Your router, is this your ISP router?
Yeah,
or
at
does it-
home.
Yeah, so it just depends. If you have a router, first of all, it's got to support you, allowing you to SSH into it.
So
if
I just have to.
yeah.
I have AT&T, so I should just research what is
Yeah,
possible.
you got to check with them.
Okay.
A lot of times if you buy if you buy a home router from Best Buy or someplace like that, some of them will let you have SSH access. I don't know what AT&T allows. I use Comcast, and I used to do my own router setup with IPv6, go get the router I wanted with all the best bells and whistles I wanted. The reason I moved away from that was anytime I have issues with the connectivity or with a setup, the ISP will usually push it if you're not using their device. And I understand why they push the responsibility on you. You got to prove it's their issue, not your issue. So they assume it's your issue, unless you prove otherwise. And that's, and that's just because they don't want to deal with the multitude of different devices that people can connect to their network.
Yeah, AT&T gives out for free.
Yeah, they
So-
give you, so so Comcast, I think it's kind of free. It might be a hidden cost, hidden fee that I'm paying per month, or, you're leasing their router. I'll have to check. I have to see if they even offer SSH as an option to me. I doubt it, because SSH usually means having a command line. And everything is browser based. So just like here, let me see if I can bring this up. We'll get, let's see if I can do this real quick here. I'll show you what I mean by that. So earlier let me actually start the recording, because that's a good question.
Recording in progress.
Let's see, did I close my Zoc? So, we're talking a little bit about SSH. I use a tool called Zoc, which I have to pay for on my Mac. PuTTY is not available, but it allows me to do SSH. Now I can do SSH from the terminal. Okay. I like this because it manages some things and makes some things much easier. But so can you SSH into your router? We're talking about this. It really just depends on whether or not the router, especially your ISP router, I kind of doubt it that they can allow you to SSH, but I don't know. I don't know. This same device here, so this is me SSHing into it, and there's certain commands I can, everything is command line, right? Show IPv6 interface brief. Okay, so this is all the IPv6 interfaces on this device. But usually your home router, of course, they're gonna usually give you some kind of web access. So here's web access to the same device that we were just looking at. Okay, this is a layer 3 switch. We'll be talking about this in my CIS-82 class. My connection is somewhere on here, one of these connections. But this is the device that, so this is usually the kind of the view that you can do, and, any kind of, information that you're going to get from it is going to kind of be more menu based. So yeah, I don't know if they allow you to SSH. Let me know. Let me know if what you find out, if you can, and I'll take a look at my Comcast router. All right, let's take a little look at ICMP v6 as far as echo requests and echo replies. Just to kind of, and I could throw a few other things in there if I can grab this screen. There it is. Okay. So this is pinging IPv4. Okay. And we can get, debug IP packet detail. So that's another one of those debug options where we can actually see the information being sent. So this is actually saying I'm sending ICMP type 8 code 0, receiving ICMP type 3 code 1. This is the echo request. This is the echo reply. So it's nice. I mean, you get to see all of this stuff when you need to see it, if you need to see it. Okay. ICMP v6 describes different things for a little bit in IPv6. It's different than IPv4. First of all, same kind of informational and error messages that we talked about in my introduction to networking class, but it also includes neighbor discovery. Okay. And that includes router advertisement messages, router solicitation messages, neighbor solicitation messages, neighbor advertisement messages, and redirect messages. Get through. So here we go. This is the neighbor discovery stuff. Okay, this is extra in IPv6. This is how we get our prefix and default gateway and Slack and all that automatic automatic IPv6 addressing stuff. This is like ARP. We just saw that. Neighbor solicitation, neighbor advertisement. Redirect message, I won't go into that, but it's very similar to IPv4. There are some different ICMP v6 doesn't contain similar error messages as IPv4, including destination reachable, packet too big. I'm going to go through some of this so I have time to show you in Wireshark here. Similar to IPv4, we have in IPv4, we have a protocol field. Protocol is value 1 when it's carrying ICMP. And IPv6, the IPv6 header, has a field called the next header field. And when it's carrying ICMP v6 message, this value is 58. We saw that in Wireshark in our previous protocols that we looked at with like router advertisements, neighbor advertisements, all that kind of stuff. So an ICMP v6 message, very similar to ICMP for version 4. Basically, it's a type code field. Okay, that's most of the information. And sometimes there's a little bit of a message body, some other information as well. We'll take a look at that. One important thing that's different with IPv6 and IPv4 is IPv6 routers do not fragment packets. Let me talk about what I mean by that. Okay, so in IPv4, there are several fields that is all about fragmentation. So what is happening with that? Let's take a look. In IPv4, if a packet is sent in some layer 2 frame, and it gets re-encapsulated at each, by the router, comes in here, Ethernet frame gets removed, new Ethernet frame gets put on. Okay, but if there's a link with a smaller MTU, and this is less likely today because now just about everything is gone with going Ethernet. Okay, but if the outgoing link is smaller than the size of the packet, meaning it can't handle a packet this size. Okay, what happens in IPv4 is it will break it up into multiple packets, as many as it needs. Now, each one of these packets will have its own IPv4 header, but the data will be smaller. Okay, it will break it up. Okay? It's like having a big box that came out of a big truck, and you've got to now transport it in a car. It's like, well, that's not going to fit in my car. You can put it in smaller boxes and put it in multiple cars, and then send that same contents of the larger box in multiple cars on its way. Now, even if this router here receives it, says I can handle packets this size, it's not the job of a router to reassemble fragmented packets. These packets stay fragmented all the way until it reaches the final destination. Okay, and it's their job to reassemble packets. This is more of an issue when we were running various layer 2 protocols and that. But now it's less of an issue. But we see here this PC will reassemble. So how much data, by the way, can an IPv4 or IPv6 packet handle? Okay, well, if we go with the standard Ethernet frame, the MTU, the size of the packet, is 1,500 bytes. So what does that look like? In IPv4, we have 20 byte header, but in IPv6, we have a 40 byte header, and that is mostly due to the larger address size. So TCP is still going to be 20 bytes. So our data with IPv4 is typically going to be 1,460 bytes for an IPv4 packet and 20 bytes less, 1,440 for an IPv6 packet. Okay. Now, what happens if the MTU of a link happens to be smaller for whatever reasons? Okay, and there's some reasons why it could be smaller, especially if any tunneling is happening, but that's not going to happen midway. I won't get into that, but there are times when sometimes packets have to be a little smaller. If this did occur, and you got to remember, all of this was designed back starting with the mid 1990s to the early 2000s. Networks were much different than they are today. Now it's mostly going to be all Ethernet. But if this did occur, so we had a packet of 1,500 bytes, what would happen is this router, instead of fragmenting it, would actually drop the packet. It would send back an ICMP, that's where we get into ICMP packet too big message back to the source, saying, hey, I'm letting you know that I had to drop your packet, and the outgoing MTU size that I need to send it is 1350. The source of the packet can say, okay, now I know, I'll send all my packets to that destination in a smaller packet size, MTU of 1350. That way they can reach the destination. So that's one of the big differences with IPv6. All right, let me jump ahead a little bit because I do want to show you this. The ICMP echo request, ICMP echo reply. All I'm jumping ahead is time exceeded message, which is like for a trace route. Doesn't change, same thing. All right, let's take a look. This is kind of cool here. And this is similar in IPv4, but I'm going to talk about an IPv6 because it's kind of cool to see it here. So when we send an ICMP echo request, okay, it's type 128 for the ICMP echo request. Okay, the ICMP echo reply is a type 129 message. I'm going to talk about these identifier and sequence numbers, and we'll actually take a look at it here. I'm going to run it up in Wireshark. Okay, so when I send a ping from the PCA to the router, okay, and in Windows, I can just say ping. I don't have to say ping 6 or ping -6 or anything like that. Sees that it's an IPv6 address because it's an ICMP echo request encapsulated in a IPv6 packet. Okay, and I got it sent 4 ICMP v6 echo requests, got 4 ICMP v6 echo replies. Let's take a look. Actually, let's do this. Let's do this live. It's always more fun. I'm going to bring up Wireshark. Okay, now, one of the things Rick always has to be careful of is I got both Wi-Fi and Ethernet running. You can see these little marks happening there, the little showing me how many. So I need to make sure that I'm running on my Ethernet. So I'm going to do that. Okay. So I'm going to capture packets on this. I can either just double click on that or go up here and start the capture. Okay. So I'm going to start my capture. Okay. Look at this, all this stuff happening. What I'm going to do is up here, I'm going to do ICMP v6. That's going to be my filter. How do you spell ICMP? You know, so that's interesting. See how it's red? That means it doesn't recognize it yet. Well, mostly because Rick can't spell ICMP. So ICMP is for ICMP v4. v6 means I want to run v6. I'm going to go over here, this arrow here, click the right arrow, filter. There we go. So I'm getting a lot of neighbor advertisements. Okay. All right. That's all right. We'll let those go. What I'm going to do is I'm going to ping that layer 3 router that we looked at earlier. Okay. That's the, so this device here allows me to get in without logging in again. Please don't make me log in again. Don't make me log in again. Come on, be nice. This is this is the layer 3 switch that I connect to. Okay. Also that I've SSH'd into. I am connected to one of these ports. I believe I'm on one of these ports here. This is also my router, my default gateway. This device also has a port, I think it's this port right here, that connects to another router. Okay. And what I'm going to do is I am going to ping. Whoops, that's not ping. It's from the terminal. Okay, move clear here. Okay, I am going to ping. Give me one moment here. I'm going to ping the interface on that layer 3 switch that I'm connected to. I'm going to ping its interface that it uses to connect to the outgoing router. Don't worry, I just wanna ping 6, this is the address, 2001, so I don't have to just ping my default gateway. Oh, well, no, that's not what it is. What is it? 260, I'm so used to doing that. 2607 colon F380 colon 80F, right? This here is the global unicast address of Cabrillo College. Okay. I don't need to use, I should use lowercase. Oops. Okay, so be consistent. Okay. Now I'm going to ping the outside interface, which is on its own network. This is the subnet that we use between that Cisco 9200 switch, layer 3 router, and the upstream router, which is a Cisco Meraki. So this interface, so this is the network. It's a /64 network. There's only 2 devices on this network. There's the other device at the other end of this connection. So the other end, so I'm going to ping this port here. It's a routed port. It's a router port. At the other end of this is the Meraki. The other end where that Meraki is a 1. But I'm going to just ping this device because I'm not sure I've got the Meraki set to answer to ping. Okay, so I'm going to ping it ICMP v6 here. Okay, echo requests. Okay, so let's take a look. Okay, all right. You just saw a bunch of stuff happening here, didn't you? Look at these. Let me stop the capture. Let's just focus on those ICMP echo requests and replies. So here's my ping. So this is coming. I want to show you the whole thing. This is my device here. This is my device here, sending an ICMP echo request to the destination. Protocol ICMP v6 echo. ICMP echo request. This is the reply coming back. Let's take a look at it. Let's just go to IPv6 header. Okay. This is my IPv6 address on my device. Okay. Temporary address. Okay. But globally routable. Can access anything in the internet. I'm pinging this address here. Oh, did I ping the .1? I guess I did. Did I ping the? Oh, I did. Okay, I pinged the Meraki. That's okay. Good. All right. I didn't know if I had the Meraki set. I pinged the .1. I was so concerned about not doing the .1 or the :1. I did the 1, but it looks like it's sending a reply. That's good. Okay, so that's the destination. Let's take and hop limit 64. There's our next header field, 58, meaning this is ICMP v6. Okay, let's take a look at it. So what am I looking at here? Look at the identifier. Okay, let's start with that. That identifier. So what that means is that for this group of ICMP echo requests and echo replies, we're going to use, my device came up with this identifier. It's kind of a random number. But what you'll notice is that's going to be the identifier that the other device is going to use in the reply. So here's the reply. So what I'm going to just show you is here's the echo request, echo reply. Here's the next echo request. So I sent 1, 2, 3, 4 of these before I broke out of it with Control-C. What I want to show you is this is how you can trace. If I had multiple pings going or multiple devices were pinging me, this identifier uniquely identifies from my client's perspective, hey, this is what I'm choosing. I want you to use this as your identifier. Tells me that this is our ping conversation. And for every ICMP echo request I send you, I'm using that same identifier. And you're going to use it back, coming back at me. So there's the echo request, echo reply, echo request, echo reply, echo request, echo reply. Same identifier. Does that make sense? Okay. All right. Next, the sequence number. Okay. This identifies my echo request to your echo reply to my echo request. So here's my echo request, sequence 0. When I got this reply back, sequence 0, that means, oh, that was to my echo request, sequence 0. Because my next ICMP echo request, I made sequence 1. So when I get this back, I know this sequence 1 is for that echo request. The next one, I sending you an ICMP echo request, sequence 2. Oh, you sent me a reply, sequence 2. Okay. So that way it knows if one of these went missing, got dropped along the way, whatever, or never heard back, it knows, and we can tell which packet got dropped. Okay. Kind of cool. Okay. Kind of an extra little thing I wanted to share with you, and that I don't talk about, so much stuff we can talk about in all of this stuff, but I wanted to just share with you, that's what this field is right here. Identifier sequence number. It's the same in IPv4 as well. Yeah. All right. And, and again, this is where I can use, by the way, I can actually, let me see if I can do this without messing up here. So I want to, so what I can do is, I can do things like this. If I wanted to just see things going to a specific destination, okay, I can right click on things and set that packet as a filter. Means I want to see everything just that packet going. So this is everything going from my device to this destination. That's an ICMP echo request. So it's just ways that you can further filter things in Wireshark. So you can kind of play around with this kind of stuff. X means get rid of all the filters. Okay. So anyway, just Wireshark is one of those things. Got my Wireshark book here, as well as I use Wireshark when I need it. And usually when I start filtering, that's when I got to look things up, figure out all these different filters. But there's a lot of good stuff here that you can filter on. Okay. And there's actually a syntax you can learn. Okay. That's very cool. All right, I'll let you go. I know it's almost about that time. We're going to talk more about, yes, Pamela, question.
Rick, thanks. I was just wondering, so next week we have class Tuesday and Thursday?
We'll have class on Tuesday, not on Thursday.
Okay, but 81 ends this week.
81 does end this week.
Okay, gotcha. Thank
Tomorrow
you.
will be our last physical meeting in 81.
Okay, got it. Thank you.
Okay, you're welcome. All right. Have a good day, everybody, and I will see you Thursday.
You too. Thank you.
Take care.
Bye-bye.
Thank you.
Recording
Good
stopped.
questions.